Welcome to 163, and this will be the first lecture of your last quarter in general physics. It's kind of exciting, I'm sure. What we're going to cover this quarter is going to be rotations and torque, and so I said bicycles and rainbows, but we should also add in some music at the end of the rainbow because we're going to do a combination of both. To start things off with, we need to talk about some just kind of fundamental definitions. We're going to tie it into the information that you're given in the first quarter of physics and kind of relate this linear to this rotational distances or accelerations and velocities, etc., etc. And so first, let's just talk about circumference. Most of you have seen this at some point in life, that we relate the circumference of a circle to this factor of 2 pi r. So r being the radius of the circle itself. So in this particular picture here, we have this little line there. Both lines denote the radius. They're equal length. So that's my radius, and 2 pi just says that the circumference, the total distance around, is related by this fixed factor of 2 pi, 3.14, the day you get to eat pie, March 14th, stuff like that. And we can relate that to this piece that we call arc length, or this distance x. So if I stretch this thing out, the thing I've done here is this, I want to look at 1/4 of a circle. So if I want to look at 1/4 of a circle, so I'm looking at 1/4 of the circumference. I can make the substitution of 2 pi r into my c, and so what do I get? I got 1/4 of this 2 pi r, and watch, magic is going to happen in the next step. Boom, pi over 2. If you remember your unit circle, 90 degrees is pi over 2. It's just 1/4 of a circle. Oh, nice. So we can write that in more generic terms than to say that I can define distances. Let's see. Oh, it's not misbehaving this time. In terms of theta r. You will also see this written as S equals theta r, where S is the arc length. Arc length. Where theta is going to be our angular displacement. You can think of it as how far, like a clock hand, is sweeping around the face of a clock. How many radians has it gone in 24 hours? So we use radians, not degrees, although you'll probably see a bit of mix of both, where we have to jump back and forth from one to the other. But in most calculations, keep in mind, we're talking about radians, not degrees. And so then, let's see, so we have this like comparison from displacement to theta, to our radians. Now what about omega? That is the squiggly W. Omega, let's see, our comparison there would be velocity. And when we discussed velocity, we said, well, one way we can think of velocity is this change in position over a change in time. Or we'd write this just more often of just delta x over t, where t is just the total amount of time to go that change. Well, if our theta is our angular displacement, how many times the clock head is being swept out, well, then the change of that, so some starting position of theta to some ending position of theta, divided by the amount of time it takes to get there, well, that is going to be our angular speed. Angular velocity, well, let's see, we have, angular acceleration. We have acceleration for linear is our change in velocity with time. So to do the same thing in rotations, if omega defines how fast we're spinning, then alpha is going to define the difference in, so our change in our rotational or angular speed over the amount of time it takes to get to that change. Now here's the question I want you to think about is if you go on a merry-go-round, if you're on your kids' playgrounds, they have the little spinning things and you can hop on them. They normally have like little poles going out, something like that, probably straight lines. And, you know, as a kid, you can like run. And I don't know why I'm drawing because I can't draw. And then you jump on the darn thing. And then your friend or sibling that doesn't care for you that much spins the wheel as fast as they can until you throw up. right? So here's the question I have for you. If you're being spun as fast as they possibly can, where are you going to go to minimize your motion sickness? Are you going to go here? Or are you going to go out here on the rim? So pause and think about it and come back. And also ask yourself why. Okay. So let's think. Our angular speed is the amount of rotations, so amount of radians per time. Are the amount of radians I'm covering, are those changing or staying the same, depending on where I'm standing? So am I covering the same amount of rotations, or radians rather, standing closer to the center of the little merry-go-round or standing out on the edge? And what I can look at, it can be like, well, from here to here, I mean, I'm going to go all the way around and come back. I'm going to cover the same amount of radians. So the radians isn't changing and the time isn't changing. So my angular speed is going to be the same for both. If my angular speed is the same for both, why is it that most of us know if you stand closer to the center of the circle versus standing on the edge, you're less likely to throw up? Where do you think that's coming from? So let's think about this thing. This tangential velocity. I should be very careful with my notation. These are tangential. So my omega and my alpha, those are fixed quantities. They will be the same no matter where you are on the wheel. What is changing is my tangential and acceleration and velocity. So depending on where I'm standing, if my omega is the same, the further out I get, the faster I'm going tangentially. That's what your eyes are like struggling to get a hold of something, because as you're out near the edge, everything is just swooshing by because you're further away from the center, from the axis of rotation. Therefore, your tangential velocity is a whizzing. So let's think about this. If I'm out here then, my V tangential is going to be, remember, this means tangential means I'm like coming straight off like this. So if my omega is the same, I have this bigger arrow here. With this one, I'm going to have this tangential velocity standing here, and it's just a small little arrow. Let me take my little stick person away. I'm going to have this smaller tangential velocity at the center. So further out I go, the bigger the tangential velocity is. I have more distance to cover. So if this whole thing is spinning in 2 seconds, I have the entire circumference to cover on the outside of the circle, where my R here, the distance I need to cover when I'm closer to the axis of rotation, is tiny. So I have this small amount of distance to go in that same amount of time. So my tangential velocity is much smaller, less likely to get sick. That's the moral of the story. Make sure your upset sibling is towards the center of the circle so they don't get ill. So we can make these translations then. Now we have a tool for saying, okay, I can go from my tangential velocity to my R, or if I know my tangential velocity and the distance away from the axis of rotation, I can also find my omega. Remember, omega will be the same for any spot on a rotating wheel. Omega stays the same. Theta and omega and alpha stay the same. My tangential velocity does not. That's the only hazard in rewriting this, is we tend to convince ourselves that they are dependent. What this is saying is that I know what my tangential velocity is, and I know my radius. That gets me to my omega, and I've defined my omega everywhere. And I can do the same thing for my tangential acceleration. You know, this divided by my radius will give me my angular acceleration. So I think I'm going to stop there and then make one video with some short examples just so you can see it applied.